Okay, I hope my screen is visible to you all.
Yes, sir.
Okay, so I think we can start. Right, so this is tutorial number 9, and in this tutorial, we will look at some problems of the unit 4. So let me start with this question number 1. So this is quite straightforward. We have been given a difference equation of a linear time invariant system. And what we have to do is we have to first of all find out a system function hz, which is yz by xz, right? That is the output by input. And this system function, then we also have to plot the poles and zeros of h of z and indicate the region of convergence. This we have also done before in the, I think, in the first or second unit, where we basically have to take the z transform. So the way we'll do it is, this is the equation that is given to us, and we will take z transform. On the left hand side we will get yz, on the right hand side, with, because there are some delay terms, so there will be z minus 1. Here there is a delay of 2, so z minus 2, and again z minus 1, and we will have these terms yz and xz. I can take all the y terms on one side and x terms on the other, and then I can take them common. So the y terms will give me the denominator, which will be 1 minus 3 by 2 z inverse and minus z raised to the power minus 2, and the numerator is simply z inverse, right? That will be the system matrix h of z, right? So which is this. Now we can also factorize the denominator into the roots, which are 1 minus 2 z inverse and 1 plus 1 by 2 z inverse. And now we have to find and plot the region of convergence for this system function h of z. So the way to do it is, we want the system to be causal. So we will select the region of convergence to be outside the outermost pole. So the outermost pole it is at z is equal to 2. So I can take mod z greater than 2 as the region of convergence. So if I have to plot this, this is the unit circle in the this by denoted by this dark line, and this is mod z equal to 2. So I've also plotted the poles, which is at z is equal to 2 and z is equal to minus 1 by 2, and there is 1 0 at because there is z inverse in the numerator, so this is at z is equal to infinity. Because at z is equal to infinity, what happens is that the system function becomes 0. So, and the region of convergence will be outside this z is equal to. So this was straightforward, the first part, which we have already seen before. In the second part, we have to find out the impulse response of the system. So again, impulse response of the system means we have to find out the inverse z transform, and so that means I have to find out h of n now. So to do that, we have this h of z. I have rewritten it here, and I can use the partial fractions a and b and the denominators. So a by first factor plus b by second factor, and it's given, and we have just calculated that mod of z is greater than 2 is the region of convergence. So then we calculate a and b by partial fractions. This would be the remaining part, and I evaluate it at z inverse is equal to 1 by 2. That gives me a, which will be 2 by 5. Similarly, I can calculate b, and then I will take the remaining part and I will substitute this root, which is z inverse is equal to minus 2. That gives me minus 2 by 5. So using this a and b, I can substitute it here, and I will get 2 by 5 times this part, the z inverse inverse z transform of this part, which will be 2 raised to the power n un. Similarly, for this part, we will have minus 2 by 5 and minus 1 by 2, raised to the power n, and then this un. So this was also quite straightforward. This was only about the z transform of the difference equation, and then we took the inverse z transform of the system function. Yeah, is there any question?
No, sir. No.
Okay, so let's look at this third part. Yeah. So let's look at this third part. This says that we have to find out a stable and non-causal impulse response. Now, what does that mean? Previously, we have calculated the impulse response of the system, but now we are asked to calculate the stable non-causal impulse response. So what that means is that if we look at this particular case, we have taken mod z greater than 2, and this corresponds to a system that is causal because the region of convergence is outside the outermost pole. But when we have to find out a stable one, so clearly this one is not stable because it does not include the unit circle. The region of convergence does not include the unit circle. So if we want to find out uh, an impulse response that is stable, we must include this unit circle. So we must change the region of convergence. So in the C part, we say that for a stable system, the region of convergence must contain the unit circle, which is mod of z equals to 1. So what other option for ROC we have? We can take the ROC between minus 1 by 2 to 2, right? Because in that case, it will include this unit circle. So obviously, in that case, we won't get a causal system because the condition of causality is not satisfied now. So we select this as the region of convergence, and we again calculate the h of n. Now what difference is there? So first of all, if we look at these two values, we have 2 and 1 by 2. So we are starting from minus 1 by 2 up to 2. That is the region of convergence. So for z is equal to minus 1 by 2, or z inverse is equal, yeah, so z equals to minus 1 by 2, what happens is that this will be a right sided sequence, and but when we talk about z is equal to 2, it will be a left sided sequence. So when we look at h of n, it will be, all of the things remain same except when we are talking about 2 raised to the power n. So for that, it is a left sided sequence because the region of convergence is up to mod z equal to 2. So we multiply it with u. So there is a u minus n minus 1 here. And similarly, now when we talk about 1 by 2, mod z equals to 1 by 2, the signal is right sided. So we will have un here. That is the only difference. Also, yeah, also one another thing is that because so the formula also changes because when we have left sided sequence, we will have minus a raised to the power n. So there is a negative sign also here, and there is this u minus n minus 1. So this is the overall impulse response for the case when ROC is this. So you see this is different from this. So that means that the system function or the impulse response depends upon our choice of the region of convergence. So that is the question number one. Let's see another question. Okay, so in this question, we have been given an LTI, discrete time causal LTI system. This is the system function h of z, and we first of all have to determine whether the system is stable. So actually, let me just ask you guys, what do you think? Is this system stable or not? Just by looking at this h of z, can anyone tell whether it is stable or not? Any ideas?
Sorry, sir. What's the question?
The question is this system stable? The first part, is the system stable? You can tell that just by looking at this system function.
Yes, sir. It's stable.
It is stable, and why is it so?
Sir, because there is a pole at point 0.9, and then the system is causal, so it will go from point 0.9 to infinity, which will include the unity circle.
Yes, correct. So, well, when we don't have to even worry about the region of convergence, simply by looking at the poles which are in the inside the unit circle, we can tell that this is stable. But yeah, definitely we also look at the region of convergence, because that is how we will calculate h of n. So if we change the region of convergence, then it might be possible that we get a causal but unstable representation. So yeah, that is correct. So there are actually two poles at point 0.9, you see, because it's z raised to the power minus 2. So yes, the answer to first one is that the system is stable because of all the poles lying inside the unit circle. So, and the second part says that we have to find out the expression for a minimum phase system H1Z and an all pass system HAPZ, such that we can decompose this H of Z into the product of these two. So I have to decompose this into one minimum phase system and one all pass system. So, first of all, the first part, it says that h of z is stable because there are poles at plus minus j zero point 0.9, which are inside the unit circle. Right. The next part is we have to decompose this h of z into one part which is all pass, and one, this is the all pass part HAPZ, and one part is the minimum phase. So for the minimum phase, the requirement is that all the poles and zeros are inside the unit circle, and the requirement for the all pass system function is that the poles and zeros occur in conjugate reciprocal pairs, right? So we must decompose this h of z into these two parts. So first of all, let us look at this h1z. It is clear that this denominator has it is within the unit circle. The poles are within the unit circle. What about the zeros? So out of these two cases, this one is within the unit circle. This is at minus zero point 0.2. So this is at inside the unit circle, but this one is not, right? So let me just first of all break h of z into this part which corresponds to everything that is inside the unit circle, and this part which corresponds to everything that is outside the unit circle. So this is clearly a minimum phase system, but this is not an all pass system, because for this to be an all pass, we must have a pole which is a conjugate reciprocal of this zero. So let me just multiply and divide by that. I'll just multiply and divide this by 1 minus 1 by 9 z raised to the power minus 2. So that way I have a pole which is the conjugate reciprocal of this numerator, right? Instead of 9, I have 1 by 9 here. And I have multiplied and I've divided and I have multiplied it with it as well. So that makes this part as an all pass part. And because this is 1 minus 1 by 9 z minus 2, which means that this the roots will lie for this part inside the unit circle only. So we can include the numerator into the minimum phase part of the system function, and the denominator helps us complete the all pass part of the system function. So that way we have obtained h of z decomposed into h1z and hapz. So this was this. Yeah, that's question number 2. Okay. Now let's look at question number 3. We have a system function. Again, we have some h of z, which is given by this. Okay. Now in this case we are given that the system is not stable and that the impulse response is two-sided. So the system is not stable, which means that it gives us some information about what the ROC might be. It does not include the unit circle. And the second is that impulse response is two-sided. What that means is that when we plot the ROC, it must be a ring, because for one point it will be left-sided and for other point it will be right-sided. So first of all, it is asking us to determine the impulse response h of n of the system. So let's look into this part first. So we have h of z given like this. We can again straight in a straightforward way calculate this using the partial fraction. We have obtained this form. We have decomposed it into three different parts corresponding to each of the poles. First thing that is given to us in the question is that the system is unstable, which means that the ROC does not contain the unit circle. The second part is that the sequence is two-sided, which means that ROC is a ring, right? So what options do we have? So first of all, we cannot have mod z greater than 1 by 2, because in that case the first condition is not satisfied, because the system will become stable. So also there is a ring, uh, ROC is a ring. So that means that we only have one option left, which is that mod of z must be between 2 to 4, because in that case the system is unstable and we get a two-sided sequence. So that's why ROC is 2 to 4. Using this, we can find out h of n. So h of n is, first of all, for when we talk about 1 by 2, it is a right-sided sequence. So 1 by 2 raised to the power n has un. For this part, it is again a right-sided sequence. So I get 28, which was the numerator, 2 raised to the power n un. Finally, this part, which has a 48, it is a left-sided sequence, so there is a negative sign here. Then 4 raised to the power n u minus n minus 1, because of the left-sided sequence. And this is the overall impulse response. Okay, now let's look at the second part. So the second part is we have to determine functions h1z and h2z corresponding to the causal and anti-causal impulse response of the overall impulse response. So this is what this means is that we basically have to try to figure out which components of the uh, impulse response are causal and which are anti-causal, and we have to put them into two different system functions. So we had this as the h of n. So the causal part correspond to all those part. So causal part is the one for which we will have h of n. So this is the causal part. Here, this corresponds to the first two values, because here h of n is 0 for n less than 0. That's why we can say that this is causal. But in the third part, you see that it's a left-sided sequence. So for n less than 0, the signal is non-zero. H of n is non-zero. So this is the anti-causal part. So for when we have to calculate h1z, which is the causal system function, we will take the z transform of these two parts. And when we have to find out the anti-causal part, which is, or sorry, the non-causal part, we will just take the system function corresponding to this part. And that's how we can obtain h1z and h2z. Yeah, that was question number 3. Okay, are there any doubts so far?
No, sir.
No, sir.
Okay, so I guess we can proceed. And I think this is the final question. Now we have been given a sequence x of n, which is the output of a linear time invariant system whose input is s of n. So the input to the system is s of n, and we get x of n as the output. and we have been given this system described by this difference equation, right? We have x of n is equal to s of n minus e raised to the power minus 8 alpha Sn minus 8, where alpha is greater than 0. And we have been asked to find the system function h1 of z, which is xz by s of z. So basically I have to simply find out, take the z transform corresponding to this difference equation, and then I have to plot the poles and zeros in the z plane and indicate the region of convergence. So first part is also quite straightforward. This is the difference equation given to us. We can take the z transform of both sides. This becomes s of z, and this becomes s of z multiplied with e raised to the power minus 8 alpha. And because of this n minus 8, we will have a delay term which is z raised to the power minus 8, a delay of 8 time steps, right? So this is now I have to find out hz, which is the output by input. So the output is x of z and the input is s of z. So I can take s of z on the left side and I will get this h1z, which is basically this part. Now, when we have to plot the poles and zeros in the z plane, we can directly see that first of all, this part is the numerator. So the zeros are at z is equal to e raised to the power minus alpha, e raised to the power j pi by 4k, right? So this is basically like calculating the nth root of unity, just like the nth root of unity lie in unit circle at 1 omega omega square. Here we have nth root lying at some circle of radius 1 by alpha, and they will repeat in a manner that we can vary k from 0 to 7. So when we have k is equal to 0, we will have z is equal to e raised to the power minus alpha as the point where uh, there is a 0. Then I vary k accordingly and I will get 8 zeros. Then when we calculate the pole, so the pole is at, in this case, we have in the denominator just 1. So we can say that there are 8 poles at z is equal to 0. So there are 8 poles at z at the origin. And when I plot this, it will look something like this. Uh, this should be a circle, and of the unit circle, this is the imaginary axis, the real axis in the z plane. There is an eighth order pole at the origin, and there are 8 number of zeros like this at a particular radius, and because of this term they are at they are at 45-degree angles. So this is how this pole zero plot will look like for this case. Also, we have to find out the region of convergence. So to find out the region of convergence, we can take uh, the one which is we can just take corresponding to, yeah, so, okay, so we can take outside the outermost pole. The outermost pole is just mod z equals to 0, so it gives me mod z greater than 0. So this is the ROC. That's the first part. Yeah. So let's look at the second part of this session. Now it says that we wish to recover S of n from x of n. So remember that we had given S of n to some system which had an impulse response h of n, and we got x of n. Now this question says that we have to recover S of n back with a linear time invariant system, and so we have to find out the system function h2z such that we can get the output yz of this impulse or sorry, of this system. The output will be actually s of n, right? And then we also have to find out all the possible region of convergence for this h2z. So what that means is that once we have obtained x of z in previous question, we now want to pass it through another system, and when we do that, we can obtain the input to h1n. So basically that means that this h2z must be the inverse of the h1z, right? So let's look at how we do this. So basic the representation is something like this. In the first part we said that we gave some s of n to h1n and we got x of n. Now we are giving this x of n to h2n, and we want the output to be the same signal that we provided originally, which means that h2n must be the inverse of h1n. In terms of the in the z domain, we can say that yz, or the z transform of the output signal, must be h2z multiplied with xz, and we want that, and we know that xz is nothing but h1z times sz. So this is the expression for yz. Now I want that h1z is equal to h2z, or sorry, h1z is the inverse of h2z, so that this part cancels out and I get yz equals to sz, or equivalently yn equals to s of n. So that's why I have selected h2z to be the reciprocal of h1z, which will be this part. Now there are two possibilities for the region of convergence. One is mod z greater than e raised to the power minus alpha, right? Because the zeros are at, or now the poles are at e raised to the power minus alpha. So that will give me a causal case, because it is outside the outermost pole, and also stable because the unit circle will also be included. I can also take mod z less than e raised to the power minus alpha as the region of convergence, but the solution I will get is neither causal nor stable. Okay, so these are the two possibilities, and this was part 2. So this should be the inverse of h1z, simply the reciprocal. And look, let's look at the third part. It says that we have to find out all possible choices for h2n such that yn is h2n convolved with x of n, which means that we have to basically take the inverse transform, inverse z transform of h2z, and we have to look at all the possible choices, and the possible choice would correspond to the possible choice would correspond to the ROC, that is stable and causal. So then we have to demonstrate by evaluating this convolution for s of n is equal to delta n. So I have to assume that the input is a delta n function, and then compute what a y of n will be. So ideally it should be the input only, so it should be delta n. So first of all, let's do this part. So I can calculate h of n by taking the inverse z transform of h2z. So that will give me e raised to the power minus alpha l evaluated at n is equal to 0, 8 and 16, and it will be 0 otherwise. Now to do that, the ROC that I have selected must be this one, and only in that case I will obtain an h of n that is that can give me the this that performs this operation, right? So if I try to do it with this ROC, I will not be able to achieve the output the same as the input, because it is not causal and or stable, right? So now let us look at whether it will work or not by evaluating it for s of n is equal to delta n. So when we give this input, we first of all can find out x of n, which was this expression, right? This is from the difference equation itself. So now I can substitute s of n equals to delta n, and I will get this part, right? Now when I pass this through h2n, I will get yn, which is the convolution of this sequence with h2n, and h2n is nothing but this is h2n. So first of all, I will get x of n, and then because there is a convolution, so once I have First of all, it will be multiplied with e raised to the power minus alpha n for n is equal to 0, and then it will be multiplied with e raised to the power minus 8n, sorry, e raised to the power minus 8 alpha, and because this will be xn minus k, so there is uh, an n minus 8 here, and this, because this is n minus 8, so it will become n minus 16. Similarly, next time, and so on, we can evaluate this convolution. And the important thing to note here is that these terms cancel out. So this term cancels out with this term. Similarly, this term will cancel out with this term, and so on. So what we can essentially say is that all of these terms cancel out and we will be left with only delta n. And that should ideally be the case because h2n is the inverse of h1n. So yn becomes equal to delta n. And that means that h2n is a valid inverse of h1n. Yeah, so that was the last question. So are there any doubts?
Excuse me, sir.
Sorry?
So in the first part of last question, you said there are 8 poles.
Okay, just a second. First part of, yeah, this one.
Sir, how there are eight
Yes.
poles at origin?
Oh yeah, so there are 8 poles. Sorry.
How there are 8 poles at the origin? I don't understand.
Okay, 8 poles at the, okay, yeah, so basically because we have this h1 of z, we assume that the number of poles are equal to the number of zeros. Now obviously there is no denominator here, so that means, but there must be 8 poles. So in that case we assume that the poles are at z is equal to 0,
Okay. So in the
right?
case
Because
of
uh, yeah, so if there were, let's say, no zeros, so basically the idea of poles is that first of all, the transfer function must go to infinity, right? So that is clear
yes,
that whenever there must be a pole, it should be at z is equal to 0 for this case, correct? And then we say that
yes,
since the poles and zeros must be equal in number, that is why there must be an order of 8 of the pole. So also
okay,
another thing that you can note is that, let's say if it was the reverse, if there was only poles and there were no zeros, then we
hmm,
would assume that there are the equal number of zeros at infinity,
okay, yeah,
right? Because at uh, yeah, so in that case, because so we have to take this assumption that the number of poles and zeros are equal, and that is why we have done this.
okay, okay.
Okay. Any other doubt?
No, sir.
Okay. Anyone else has any doubts?
No, sir.
Okay. So I guess we can end this tutorial then. Thank you. You can, I guess you can leave.
Okay.
Thank you.